Hello everyone, my name is Sunny and I will be talking about mechanisms and arrow pushing. There are four patterns of arrow pushing: the nucleophilic attack, loss of leaving group, proton transfer, and carbo-cation rearrangement. The first pattern is the nucleophilic attack, characterized by a nucleophile attacking an electrophile. In the first example, chloride is the nucleophile and the carbo-cation is an electrophile. In this case, the attack only involves one arrow from the lone pair to the electrophilic center of the carbo-cation, which results in a bond forming between the carbo-cation molecule and the chloride. It is also common for a nucleophilic attack to utilize more than one curved arrow, which brings us to the next example. The first arrow starts at the lone pair of the nucleophile and attacks the electrophilic center. The other arrow is simply a resonance arrow from the pi bond to the oxygen, like so. The second pattern is the loss of leaving group, characterized by the loss of the leaving group. In the first example, bromide leaves the molecule, making a carbo-cation and a bromide ion, like so. The second example shows how loss of leaving group can have multiple arrows. First, the curved arrow starts with one on the lone pair of the electrophile and ends up making a pi bond with the neighboring carbon, which results in the bromide leaving, like so. Okay, now on to the third pattern, which is the proton transfer. This is characterized by only two earth arrows. It's always going to be two. In the first example, the ketone is protonated and the two curved arrows are drawn from the ketone to the proton. And the second one shows what happens to the electrons that were previously holding the proton. So from the lone pair, and the bond to the oxygen. And sometimes proton transfer are shown with only one curved arrow. This is because chemists are lazy. In this case, the base is removed, so the proton is not shown. This can be used on exams and other standardized tests, so better watch out. Like so.
And now we move on to our fourth mechanism, carbo-cation rearrangement. First, let's take a look of why this mechanism works in the first place. As you can see here, we have a structure that has a hydrogen and a carbo-cation charge. As you can see here, they're in the same p orbital, so they can easily switch places. When they do switch places, there's a carbo-cation in the place of the hydrogen. Next, we'll see when this mechanism needs to occur. So carbo-cation is basically all about stability. And how we know what's stable is how many carbons are attached to them. As you can see here, there's only one carbon attached, so we call this a primary. Here we have two carbons attached, secondary. And the most stable is going to be tertiary. So one more thing we need to know is how we can make carbo-cation rearrangement happen. We can use either a hydride shift or a methyl shift. But first, we'll take a look at the hydride shift. We can see here in this example where the carbo-cation is at originally. It's over here, and as we know, it's primary, which is the least stable. So what could we do to make it more stable. As the name implies in Hydride Shift, we'll be using the hydrogen, and we could be moving it to where the carbocation is at. So now, the carbocation is surrounded by 3 carbons, making it tertiary, much more stable. We could also use Methyl Shift, which is very similar to Hydride Shift. In this case, we have a carbocation, again, primary, but we could move a methyl group to this side, and now the carbocation is tertiary. Now we use the example and see what we should do to make this carbocation rearrangement a more stable one. Right here we start off with a secondary because we could see that there's 1 carbon and there's another carbon attached to it. And as we move a hydride, which is the best choice in this scenario, we'll get this structure first. And now we have a tertiary because it's surrounded by 3 carbons. However, since this is resonance, we could keep on moving electrons. So we have another structure, which becomes this. But this goes to being primary, even worse than the secondary. So we're not going to be using this one in many cases. We'll just be focusing on this one.